Time to get started with some rigid body mechanics. That's the objective of the class today. We'll get initiated, inducted into this new area, and easy little thing, but has to be done in stages. You've gone through these concepts in school, for school, not in school. And you might have had some vague, hazy ideas about, what was going on there. Somehow you might have managed your school exam as far as this topic is concerned. But then, I will assume you know nothing and build it up from scratch for you. So, the moment I talk rigid body mechanics, essentially, you know it as rotational motion. So, first of all, what's a body? It's just a collection of particles. And those collection of particles, like you've already seen, could be available in a discrete format, a discrete collection, or a continuous collection. Right? By this time, you're already familiar with what a discrete collection of particles is and what a continuous collection of particles is. But then what about a rigid body? A collection of particles, all right. But let's understand what a rigid body really means. So, when I talk of a rigid body, then what I'm seeking is that I'm picking any two particles of the rigid body. Let's say this is a certain particle 1 and this is another particle 2. At a certain instant of time. At a certain instant of time, there is a particle here and a particle here, part of a bigger rigid body. All right. This is the line joining the two particles. This is the line joining the two particles, right? Let's say on the rigid body, you created a scratch between 1 and 2. All right. So this was like a scratch between 1 and 2. While the rigid body is in a state of, let's say, very general motion, very complicated motion, say, the scratch moves and reorients. The scratch moves and reorients in general. So after a while, the scratch joining 1 and 2 might look like this, might have moved to this position, would have got reoriented like this. After a while, the scratch could look like this and could look like this, and so on and so forth. Right? Now, the position of 1 changes, the position of particle 1 changes, the position of particle 2 also changes, right? The scratch joining 1 and 2 would bodily move to another position, would also get reoriented, would also get tilted, right? Everything happens during the journey. But one thing doesn't happen during this entire transition. The separation between 1 and 2 remains unaltered. The separation between 1 and 2 should not change with time. That's the rigid body consideration. The rigid body consideration is that the separation between the two particles will remain the same. This you can refer to as the relative separation between 1 and 2. This is referred to as the relative separation between particle 1 and particle 2. Right? This is R, this is R, this is R, this is R, and so on and so forth. Right? Clear? Fundamentally, if this compliance is true for any pair of particles of the rigid body, then the collection of particles is said to be a rigid body. That's when the collection of particles is said to be a rigid body, if this compliance is met by any pair of particles constituting the body. Clear? Now, what would lead to this then? Different particles constituting the rigid body need not necessarily have the same velocity. They are entitled to different velocities. They could, in general, have different velocities. Even at a given instant of time, different particles constituting the rigid body could have different velocities. Say at a certain instant of time, the velocity of one is, say, v1, and say it makes an angle alpha with the line joining 1 and 2, right? And say the velocity of 2 is v2, and it makes an angle beta with this line. Right? Now, if I resolve the velocities of 1 and 2, then the velocity of 1 perpendicular to the relative separation is going to be v1 sine alpha. Parallel to the line joining 1 and 2 would be v1 cos alpha. For particle 2, v2 sine beta, v2 cos beta. Right? These are velocities perpendicular to the line joining the two particles. These are velocities parallel to the line joining the two particles. Now, if v1 cos alpha is any different from v2 cos beta, then the separation between them will change with time. Right? If v2 cos beta is different from v1 cos alpha, then the separation r would change with time. Yes or no? But the separation r is not supposed to be changing with time no matter what. Right? So in order to preserve r at all times so that the rigid body considerations are maintained, what is important is that v1 cos alpha must be equal to v2 cos beta. That means velocity of 1 along 1, 2 must be the same as velocity of 2 along 1, 2. That means their relative velocity along r must be 0. That means their relative velocity along the line joining the two must be 0. Yes or no? So what it really means is vrel along 1, 2 must be 0. Relative velocity along the line joining the two particles must necessarily be 0. For this to be a rigid body, take any two particles at a given instant of time. Their relative velocities along the line joining, their relative velocity along the line joining the two must necessarily be 0. Got me? So v1 cos alpha must be equal to v2 cos beta. v1 cos alpha minus v2 cos beta, which is the relative velocity, that must necessarily be 0. This essentially is the rigid body considerations expressed in a kinematic standpoint. This is the kinematic standpoint of a rigid body. This is the kinematic standpoint of a rigid body. Kinematic standpoint. Right? Now, yes, please. I'll come to that. I'll tell you what that does. That need not be the same. That need not be the same. See, it's because if this was also the same as this, then the amount by which one moves up is the same as the amount by which two will move up, and there would be no reorientation produced, isn't it? If v1 sine alpha is the same as v2 sine beta, what would happen? In a given time, the distance by which one moves up would be the distance by which two moves up, and 1, 2 would move parallel to itself. But that need not necessarily happen. If v2 sine beta is different from v1 sine alpha, then the line joining 1, 2, the scratch 1, 2 will reorient itself with time. Yes or no? Right? This being the perpendicular components being different would cause the scratch 1, 2 to reorient itself with time. That's the objective of this being. So if it's not reorienting itself with time, then V2 sine beta must be equal to V1 sine alpha. But in a very general sense, need not be the case. That's not a requirement for a rigid body.
So if it's not equal, then the separation would change. Yes, sir. No.
Of course not. Why would the separation? Or if they are different, say one moves to this position and 2 moves to this position, this R will remain the same. Why should the separation is only about, separation would take place if there is velocity of 1 in this direction different from velocity of 2 in this direction. Perpendicular components will not change the separation between two particles. No, relative separation is about relative velocity along the line joining the two. Please, yaar, come on. Of course not. I mean, if this is different from this, will not cause the line joining 1, 2 to change with time. The distance between 1 and 2 will not change with time. That will change only if this velocity is different from this velocity. That's when they would come closer or move further away. I mean, I don't want to get into that discussion at all because that's so obvious, evident. Only velocities parallel would cause the separation to change with time. Please. Okay, is that okay or not? What if V1 sine alpha is V2 sine beta? This would move upwards. The scratch would move upwards without reorienting itself. Translation. Pure why diagonal, yaar? Why diagonal? If V1 sine alpha is V2 sine beta, then the amount by 1 was originally here, 2 was originally here. In a given time, this moves by a certain distance ds, 1 comes here. 2 will also move by the same distance ds, and 2 will come here. This will constitute a rectangle. This r will remain the same. 1, 2 is moving parallel to itself then.
No, diagonal as in like there's a component, so it is.
What component?
The V1 cos alpha and V2 cos beta. So
They are the same. They are the same. In a rigid body, V1 cos alpha is the same as V2 cos beta. So this length will not change with time.
And sir, if they were same but V2 sine beta was directed oppositely, then the particle
Does not matter if... Look, say V2, the perpendicular velocity of this was like this, the horizontal velocity of this was like this. The perpendicular velocity of this was like this, the horizontal velocity of this was like this. Peace. Then all that would happen is 1, this is 2, this would go down, this would move up. This line joining 1, 2 would go this way. That's all.
so if both are equal, the perpendicular components are equal.
Does not matter. Then the amount by which this would have gone up is the amount by which this would have gone down. This distance will be equal to this distance. This was the original line joining 1 and 2. Isn't it? Then this distance will be the same as this distance. Yes or no? Is that okay? All right. Now, right, see, I'll tell you, even I'm not averse to you bringing up your queries, but even before that, you know, spend a few seconds thinking about it. Few seconds, that's all. Now, the kind of different kinds of things a rigid body could execute. Say, this is a certain rigid body, right? Composed of several particles. All right? there is a center of mass of this rigid body. There is a center of mass of this rigid body. Now, this was the velocity of the center of mass. This was the velocity of the center of mass, right? Now, if every particle constituting the rigid body had the same velocity as that of the center of mass, if every particle constituting the rigid body had the same velocity as the velocity of the center of mass, then what would happen is this structure after a while would come to this position, parallel to itself. This would have moved parallel to itself, where each particle shares a velocity in common with the velocity of the center of mass. Every particle has the same velocity as the velocity of the center of mass. Even though the velocity of the center of mass could change with time, but at any given instant, if VCM is the velocity of the center of mass, then VCM would be the velocity of all particles constituting the rigid body. The center of mass could be accelerated. But then, if VCM has changed, so would the velocity of all other particles, right? So, in this case, for example, the rigid body has moved parallel to itself, where every particle constituting the rigid body has the same velocity at all times, right? At a given instant, all the particles share a common velocity with the velocity of the center of mass. This kind of a motion is referred to as pure translation. This motion is referred to as pure translation. Velocity of every particle is the same at a given instant and is equal to the velocity of the center of mass, then the motion is deemed to be pure translation. Pure translation. Right? The body is not getting reoriented with time. The body is not getting reoriented with time. The other kind of motion could be, if this is a rigid body and it is constrained at a point, in the sense it is fixed, nailed or pivoted at a point. Say there is a point H which is called the hinge. The rigid body is hinged at the point H, fixed at the point H. H is therefore permanently at rest. H is a point on the rigid body which is permanently at rest, right? It's called the hinge. It's called the hinge. Now when this happens, and I look at, let's say, a particle I of the rigid body, then at a distance Ri from the hinge, then the only kind of motion this particle I could execute would be circular motion centered at H and of radius Ri. Any particle I would move in a circle centered at H and of radius Ri. If there is a point which is permanently at rest, H is a point which is permanently at rest, then any other particle, let's say I, the only kind of motion it could have is a pure circular motion centered at the hinge and of radius Ri, where Ri is the distance between the particle I and the hinge H. Yes or no? Right? Isn't it? See, if this is the hinge and this is the particle I, then the only kind of motion it could execute would be circular motion of radius Ri centered at the hinge. Of radius Ri centered at the hinge. Right? That means this particle would have a certain angular velocity. This particle will have a certain angular velocity associated with this particle. Right? There is a linear or a tangential velocity associated with this particle. Vi then would be Ri omega. Vi then would be Ri omega. Right? The velocity of this ith particle, where the Vi would always be perpendicular to Ri. Right? So every single particle then constituting the rigid body will move in a circle centered at H, the hinge, but in general of moving in circles of different radii. Moving in circles of different radii. Right? That means the other thing is, let's say this is a rigid body, say hinged at H. Okay? And I look at, say, a particle I, which will move in a circle of radius Ri, and I look at a particle J, which will move in a circle of radius Rj, then do you realize after a while, if I is here, J would be here. Yes or no? If I has described this arc, J would describe this arc, and both would have described the same angle theta at the center. Both particles I and J would have described the same angle theta at the center. Right? In the same time, if they have described the same theta at the center in the same time, they must have the same omega, angular velocity. So every single particle of this rigid body will have the same angular velocity. So omega will remain the same, the angular velocity will remain the same for every particle in this kind of a motion. Omega will be the same for every particle constituting the rigid body in a motion of this kind, where there is a certain point H which is permanently at rest, referred to as the hinge or the pivot. Linear velocity is r into omega, yaar, pure circular motion. If omega is the angular velocity, v is r omega. Circular motion, I have done that. I have spent a class doing that in circular motion. If omega is the angular velocity, linear velocity is r omega. Please, yaar. Have I done that before? So every single particle has the same angular velocity. Every single particle has the same angular velocity. Now, however, since different particles move in different RIs, the linear velocity would be different for different particles. The linear velocity will be different for different particles in general, but omega will be the same. Angular velocity will be the same. So this body moving in a manner where every single particle has the same angular velocity, moving in concentric circles, different particles are moving in concentric circles because they have a common center edge. In general, moving in circles of different radii, the motion is then referred to as pure rotation. This motion is referred to as pure rotation. This motion is referred to as pure rotation. Right? And we say this is then referred to as the axis of rotation. This is called the axis of rotation. Perpendicular to this body passing through H, this is called the axis of rotation. This is called the axis of rotation. The axis of rotation can be obtained. See, again, when it comes to angular velocity, this, for example, we in common parlance say is clockwise angular velocity. But clockwise, anti-clockwise is not direction. That's only sense. That's only sense. But then, you know, there has to be something about the direction of omega. What's the direction of omega? Although in most cases, we are okay dealing with the sense of omega. But then you should also know, if the sense of omega is clockwise, then there must also be a direction associated with omega. The way to obtain the direction of omega is take your right hand, curl your fingers in the sense of omega. Curl your fingers in the sense of omega and observe your thumb. The thumb goes into the plane of the board. The thumb goes into the plane of the board. So the direction of omega is perpendicular to this, right? And that will also give you the axis of rotation. That will also give you the axis of rotation. Clear?
Sir, if each particle will have different omegas, then also it will be rotation.
No, it will not be pure rotation. How can each particle, if one is hinged, permanently hinged, how can is it possible, and if this is a rigid body, is it possible that I describes a circle, but J does not come to this point and J comes here? Then the separation between I and J will change with time. It will no longer be a rigid body. They have to describe the same angle theta. So they have to necessarily have the same. That's actually the cardinality about pure rotation. Every single particle of the rigid body must have the same omega. Must have the same omega. Clear? Now, there could be a motion of the following kind of a rigid body. Like I told you, if the rigid body comes to this position, where all that is important is the velocity of the center of mass, this was pure translation, right? This was pure translation. If it was hinged about a certain point edge, which need not be the center of mass, then this particular line, for example, after a while will look like this, right? This would be the orientation of the rigid body after a while. This line, this central line would come here, then it would have got reoriented to the extent of theta, right? And this is pure rotation. This is pure rotation. Now, a very general motion could be the following. Can I wipe this off? A very general motion could be the following. There is this rigid body. This is the center of mass of the rigid body. After a while, this is where the rigid body is. This is the center of mass. Now, two things have simultaneously happened. A bodily movement of the center of mass, which represents translation, right? Which is a measure of the extent of translation that took place in the rigid body, the bodily movement of the center of mass. That can be used to measure, that's one way to measure the extent of translation that took place in a rigid body. Then, the other thing is, realize that this is a certain line. I copy paste this line here, parallel to itself. This was the central line, new central line. This was the old central line. This was the old central line, and say this is the new central line. That means now old central line and the new central line include a non-zero angle theta, include a non-zero angle theta, and this measures rotation produced in the rigid body. This measures reorientation produced in the rigid body. That means it has undergone pure translation and it has undergone pure rotation simultaneously. Simultaneously, the body has continued to move in this direction and has got successively reoriented while getting translated. While getting translated, it has got reoriented with time. That means there is simultaneous presence of pure translation and pure rotation about the center of mass. This motion could be imagined to be as follows. It's as if this happened first. Just to superimpose, to get an idea, it's as if this happened first, the body got translated. This is the center of mass, the body got translated first, say. Right, it just translated first. And then what happened was, hinged about the center of mass, it got reoriented. Hinged about the center of mass, it got reoriented. Right? It's as if two independent processes have occurred on the rigid body. One, pure translation, let's choose to measure you can draw a better figure, huh? Let's choose to measure this by the motion of the center of mass particle. This is only a convention. You could use other particles also to measure pure translation, right? There is no compulsion for you to measure pure translation by using the center of mass particle alone. Life only becomes a little simpler if you choose the center of mass particle as a reference particle. There is no loss of generality by choosing the center of mass particle though. Okay. Plus, hinged about the center of mass, pure rotation, hinged about the center of mass, pure rotation. It's as if you moved it to this position and then you fixed it at the center of mass. You hinged it at the center of mass, pivoted, and then reoriented. That was pure rotation. So this is the combined effect of pure translation and pure rotation about the center of mass.
So, but for it to be pure translation, the velocity at the uppermost point and the lowermost point should be the same also as the center of mass.
That was if it was only pure translation. Now I am saying it's the combined effect of pure translation and pure rotation. It's not just pure translation. It's as if first, to get to this position, I could do two things. First, move it here. Now the velocities is the same, but actually it was not pure translation. It also had to get reoriented. Now I hinge it at the center of mass and I reorient it. It's not that there actually is only translation. If there was only translation, then what you said is right. But there is actually reorientation that also occurs. So the velocity of the topmost point and the bottommost point is not the same, because otherwise it will not get reoriented. No, that's exactly what I've been telling you. This is our choice. We choose to measure translation by the center of mass, and then we imagine that pure rotation is occurring as if I have hinged it at the center of mass and reoriented. But I need not stay confined to the center of mass to cause this to happen. I can choose any other particle to represent my translation and hinge the body about that particle to reorient it and cause pure rotation. Right? Its center of mass is chosen only out of some convenience in the algebra that is produced down the line. That's all. But it need not get needlessly restrictive on that front at all. You know what I'm saying? Right? Do you all understand this? Right? So, pure translation measured by the bodily movement of the center of mass. Then, hinge about the center of mass, pure rotation measured by that. As if I've hinged the entire rigid body about the center of mass and reoriented it. That will measure omega. That will measure omega. Right? The motion of the center of mass will measure translation, VCM, and the extent to which this line gets reoriented would measure the omega of the rigid body. Is that all right or not all right? So now this kind of a motion, which cements pure translation and pure rotation in one single position, is called combined motion. This motion is actually called combined motion. Or sometimes referred to as general rigid body motion. Combined motion or general rigid body motion. Right? It's the superimposition of pure translation with pure rotation. That's general motion or combined, general rigid body motion or combined motion. Either way. Okay. Questions? You have questions? No? Now, our endeavor here is to examine general rigid body motion, combined motion, the various effects associated with it. That's what we'll explore. Clear? Now, say this is a rigid body. But before that, let me tell you that even though we've defined translation measured by VCM, there is need to address what is exactly meant by omega of a rigid body, right? Because, you know, the pure rotation effect would be measured by the omega. But then, you know, we need to be very clear in our understanding of what omega really means for general rigid body motion. We have to very precisely understand what omega means for a rigid body, right? Because there actually is no center about which it's rotating. I'm only superimposing the two effects to make life simple, but then for omega in general rigid body motion, angular velocity in general rigid body motion, there is nothing like, you know, a point about which I would, at least to begin with, you know, we don't have necessarily a center. Down the line, we'll create notional effects. We'll also look at a prospective point about which it could be imagined to be in a state of pure rotation, even in general rigid body motion. But even before I venture into that, let's, in a very simplistic, rudimentary manner, understand the implication of omega of a rigid body in general motion. In general motion, what omega means in a rigid body needs to be addressed. Okay. Now, physically, conceptually, if this is a particle 1, this is particle 2 of a rigid body, right? And I created a scratch. There's a scratch that I created on the rigid body joining particle 1 and 2. Okay. Now, if there was no omega on the rigid body, then at different times 1, 2 would all be parallel. The scratches would run parallel. If there was no omega, this is what would happen. This scratch, the body is moving, but the scratch 1, 2 is always parallel to the original position. Right? That's when I say there is no omega associated with the rigid body. That's when I say there is no omega associated with the rigid body. No omega in this case. No angular velocity possessed by the rigid body if this happens. Right? However, if after a while you find one to be here and 2 to be here, right? This is the new orientation of the scratch 1, 2. That's the new orientation of the scratch 1, 2. The original orientation, if I copied and pasted here, this was the original orientation. I just copied this and pasted it here, parallel to itself, right? This was the original orientation of the scratch. This is the new orientation of the scratch. Do you then realize that there is an angle theta by which the scratch has rotated in a given time? There is an angle theta by which the scratch has rotated in a given time, right? And this theta, rate at which this theta changes with time, rate at which this theta changes with time is a measure of the angular velocity of the rigid body. The rate at which this theta changes with time is a measure of the angular velocity of the rigid body. Very bubbly ringtone. Got me? Now, so this is the generalized description of omega of a rigid body. This is how the omega of a rigid body gets measured. Now, to get more detailed about the measurement of omega of a rigid body at any given instant of time, say at a given instant of time, the point 1 was here, the point 2 was here, say. At a given instant of time, let's say this is where the scratch was. Okay. Particle 1 had a velocity v1 making an angle alpha with the line joining 1 and 2. Right? Particle 2 had a velocity v2 making an angle beta with the line joining 1 and 2. Right? This is like I told you, the parallel components v1 cos alpha and v2 cos beta. These are the parallel components. The perpendicular components are v1 sin alpha and v2 sin beta are the perpendicular components, right? Now, the relative velocity in this direction is 0, so v1 cos alpha is the same as v2 cos beta. That's a requirement for the body to be rigid, right? Now, in a small time dt, this is 1, this is 2. In a small time dt, see, the displacements of 1 and 2 in the horizontal direction would have been the same. But now let me examine the displacements in the vertical direction in a small time dt, right? In a small time dt, say the displacement of 1 would be v1 sine alpha dt. The displacement of 2 in a small time dt is going to be v2 sine beta dt. Yes or no? This is where 1 is, this is where 2 is. Yes or no? Right? Therefore, this becomes the new orientation of 1, 2. This becomes the new orientation of 1, 2. Right? The amount by which 1, 2 has rotated is this. This is the amount d theta by which 1, 2 has rotated. Yes or no? This was the original position of 1, 2. Now this is the revised position of 1, 2. It has got reoriented to the effect of theta. D theta, right? Now, this d theta dt will measure omega of the rigid body. This d theta dt will measure the omega of the rigid body. The amount by which it has got reoriented divided by the time it to get reoriented to that extent. So, omega will be measured by d theta dt. Now, tan of this angle would be this length divided by this length. This length is r. The separation between 1 and 2, this will remain practically the same. This is small change, right? See, this is almost like a circular arc. This is almost like a circular arc, and this is the chord length. This is the chord length. See? This is almost like a circular arc. This is almost like a small circular arc subtending an angle d theta at the center, and this is the chord length. Chord length is approximately the same as arc length. So this length, as you can see, is v2 sine beta minus v1 sine alpha dt is this length. And you know, this is approximately the same as this, the radius of the circle described. If this is r, this is also approximately r, because this is a small angle. This is a small angle. So now this length is r d theta, Yes or no? Confused kya? No, just because I got a little irate with a few things doesn't mean that you will refrain from asking questions. You can still pose questions. Just take a breath before you pose so that you know. Do you understand this? Do you all actually understand this? So then d theta dt is available from these considerations. D theta dt then is rendered v2 sine beta minus v1 sine alpha divided by r, which means this is relative velocity in the perpendicular direction. Yes or no? This is relative velocity in the direction perpendicular to r divided by r, right? So this is omega. The angular velocity of the rigid body is then measured by, take any two particles can be used to do this calculation. Just one moment please. Any two particles could be used to do this computation. It's not like you have to stay confined to one pair. Any two particles could be used to do this calculation. You can say relative velocity perpendicular to the line joining the two particles divided by the separation between the two particles will measure the omega of the rigid body. So perpendicular components, difference in the perpendicular components will produce omega. Difference in the perpendicular components will produce omega. If the relative velocity perpendicular to the line joining the two, this is the relative velocity perpendicular to the line joining the two particles. If this is 0, then omega will be 0. Right? Yes or no? So omega is measured. So whereas the velocities along the line joining 1 and 2 is the same, the velocities perpendicular to the line joining the two may or may not be the same. If they are the same, then it's a case of pure translation. Omega will be 0. Else, if they are different, this will result in production of omega or reorientation of the rigid body. So, if one has knowledge of the velocities of any two particles constituting the rigid body, one can obtain the omega of the rigid body. If you have knowledge of the velocities of any pair of particles of the rigid body, then the omega associated with the rigid body could be obtained. Yes, you got it? That's what I said. I should procrastinate answering your questions by a few seconds. I think that will do the job. Clear about it? See, it's a very nice, fantastic topic and not difficult at all. I'll make sure that you understand everything about it, except if you do not know V is R omega by this time, then that's very disappointing. You know, end of class 11, V is R omega should be known by every living soul, even if you have taken commerce. Do you get this right? Huh? So the way to look at it is it's as if this situation could be reduced to, it's as if I treat one as the observer at this instant of time. That means if one is looked upon as an observer, then the velocity of one is 0. Right? Now, using 1, I observe 2, particle 2. Then what would I see in 2? If 1 is the observer, what would 1 report about 2? What would be the velocity of 2 reported by 1 in this direction? 0. So 1 would velocity on 2 in this direction. Velocity of 2 as seen by 1 along this direction, along 1, 2. Parallel direction. Along the parallel direction must be 0. Right? What would be the velocity of 2 reported by 1 in this direction? V2 sine beta minus V1 sine alpha. Right? V relative perpendicular is V2 sine beta minus V1 sine alpha. And this is the separation between the two. Yes or no? Right? So it's as if one describes the motion of 2 at this instant of time to be circular. At this instant of time, one describes the motion to be circular, centered at the observer 1 and of radius r and of tangential velocity or linear velocity equal to this much. One would report on 2 a velocity like this. One would think, because 1 is like an observer, it's fixed. So one would think that 2 is moving in a circle of radius r with a linear velocity like this, centered at 1. And therefore it would say, alright, relative velocity perpendicular would be r into omega. R into omega. Right? So omega is perpendicular relative velocity divided by r. So any two particles constituting the rigid body could be used towards computation of omega. Could be used towards computation of omega associated with the rigid body. Right? So again, not restrictive in any sense. Not restrictive in any sense. Right? And this omega itself could change with time. This omega itself could change with time. And the rate at which this omega changes with time is referred to as alpha, or the angular acceleration. Got me? Rate of change of omega with time is angular acceleration. Do you all understand this? Hmm? Sometimes, you know, when questions of this kind emerge in the class, V is R omega, it's not that, and around this time, it's not that I'm annoyed with you, I'm actually terribly concerned and disheartened, because then suddenly, you know, everything is reduced to cipher. It's nothing. You have also appeared for your class 11 promotion tests. But I have proved that also in the class. Now if I use a plus b whole squared is a squared plus 2ab plus b squared, and even for that you ask me for a proof, you know, that will result in a, I mean, we will need to spend 10 years towards preparation of IIT JEE. After that you will be not eligible for the exam. That's the only problem. I don't mind teaching you for 10 years. You would then become a teacher than a student after 10 years of preparation. Is that okay or not okay? I'm still not able to come out of your question, you know. I'm affected. This off. Sometimes I feel people ask this question out, that may not, I want to give you the benefit of doubt, but on occasions I would also look at it with a lot of skepticism and look upon it as a prank than any genuine question. So suppose there was a rigid body and it had a velocity, there was particle 1 and particle 2. If Vx was the velocity of particle 1 in this direction, what would be the velocity of particle 2 in this direction? Vx, right? Suppose the velocity of particle 1 in this direction was V1 and velocity of particle 2 in the perpendicular direction was V2, and R was the separation between the two particles. Then what would be the omega of this rigid body in which the velocities of the two particles is shown? Right, it will be plus. Relative velocity would be V1 plus V2 perpendicular. Yes or no? V2 plus V1 by R would be the omega. And this would be, do you realize that this would be the sense of omega? Because 1 would go up, 2 would go down. Then this would obviously be the sense of omega. So every time the sense of omega would have to be determined out of common sense. Okay, don't use formulas to determine the sense. Clear? Is that all right? Now, if this was a rigid body, then it's the combined effect of pure translation and pure rotation. Pure translation and pure rotation. See, it's as if, you know, you are sitting in the train and the train is stationary. Okay. And when the fan moves, then the fan is like in a state of pure rotation. If you are an observer, the fan moves in a state of pure rotation. You are sitting inside the train. Okay. Now there is an observer outside, right? When the train is stationary, he would still report the motion of the fan to be pure rotation. Now when the fan continues to rotate, and the train moves, then the person sitting outside would report combined motion, would report combined, whereas you sitting inside would still report pure rotation. Got me? Now, two things then that would stipulate comprehensively general motion or combined motion. Something that would characterize translation, which is the center of mass, VCM. VCM would characterize the translation or the pure translation effect produced in the rigid body. Then there is an omega associated with the rigid body, by virtue of which it keeps getting reoriented, with time. So there is an omega associated with the rigid body, which will reorient the rigid body, and I have already told you how to compute the omega of the rigid body, right? Now, there is a particle P. Say, it's located at a distance r0 from the rigid body. It's located at a distance r0 from the from the center of mass, r0 from the center of mass. And I want to be able to compute the velocity of this point P. Given VCM, given omega, and given the exact location of P. See, P would be known out of, let's say, if r0 is known, and say if theta is known, then the position of P would be known, right? So P is known, one way or the other, the position of P is known. In this state of the rigid body, where the center of mass has a velocity VCM and the rigid body has an angular velocity omega, I wish to compute the velocity of a certain point P whose position is given to me, right? Now the way to do this is, we would superimpose pure translation with pure rotation. That means this motion could be looked upon as a linear combination. I may not be able to exactly draw the rigid body the way it is here. And I made a mistake by drawing it so irregular. If I had drawn it more regular, then it would, but then the intention is to almost replicate this. Okay. So then, one is where every single particle has a velocity equal to the velocity of the center of mass. That means, because of pure rotation, the point P would have a velocity equal to velocity of the center of mass. Because of pure translation, the point P has a velocity which it shares in common with the center of mass. Plus, imagine it to be hinged about the center of mass. Imagine it to be hinged or pivoted about the center of mass, and put it in a state of pure rotation with an angular velocity omega about the center of mass, right? That means this is pure translation. Every particle has a velocity equal to the velocity of the center of mass plus pure rotation about the center of mass. That is hinged about center of mass, that is hinged about the center of mass, pure rotation about the center of mass, right? Now, so the combined effect of these two will produce this combined motion or general rigid body motion. Okay. Now, because of the pure translational effects, point P would inherit a velocity VCM from the center of mass, right? Because of pure rotation, the point P would move in a circle of radius r0 centered at the center of mass as shown. It would then, if it's moving in a circle of radius r0, it would have a linear velocity or tangential velocity Vp, which is r0 omega right. So the point P has a velocity VCM which it shares with the center of mass because of pure translation. Then it has a velocity perpendicular to r0. It has a velocity perpendicular to r0 because of the effect of pure rotation about the center of mass, and the velocity would be r0 omega as shown. Yes or no? Do you all understand this? So then, let me get back to this. The net velocity of the point P then, the point P, VCM because of pure translation and a velocity perpendicular to r0, r0 omega. This is the velocity profile of the point P. It has a velocity VCM like this, and it has a velocity perpendicular to r0 because of pure rotation about the center of mass as shown. The net velocity of the point P then would be the vector sum of VCM and r0 omega. Vector sum of VCM and r0 omega would be the net velocity of the point P. That means the point P, Vp like this, it has a velocity r0 omega like this. The resultant of these two velocities would be the net velocity of the point P. Sorry, this is VCM. This is VCM. The resultant of r0 omega and VCM would be the net velocity of the point P, whose location is given to us. Right? And this you could do for every single particle of the rigid body. This you could do with every single particle of the rigid body, yes or no? Right? So given VCM and omega, I have at my disposal the velocities of every single particle constituting the rigid body. How about it? Right? I therefore have access to what's referred to as a velocity field. I therefore have access to what is referred to as a velocity field, right? Right? The collection of velocities of all particles constituting the rigid body can be obtained by the knowledge of three things: VCM, omega, and the position of that point. These three things would come together to tell you the net velocity of any particle P of the rigid body. Right? Clear? Now, so far so good. Clear? In fact, what we do is, see, if most of the things that we would deal with would be planar. In general rigid body motion, planar motion. So this would be like a lamina or the effect produced by a lamina, right? Laminar. Most of the bodies would either be actually laminar in character or would have the same effect as that of a lamina, right? So now what we actually do is, by a combination of VCM and omega in a manner that I described, even if P was a point outside the rigid body, we in fact imagine that the lamina extends through the entire plane, right? So that even if P is outside the lamina, I could obtain the velocity of the point P by suitably combining VCM and omega. right? So with every single point, using VCM and omega, I can obtain either a real velocity of a point P if it is on the rigid body, or extend the laminar to include a point outside the rigid body, then I can associate a velocity even with that point. You know what I'm saying? So there is a velocity field in the entire plane that I can talk of, just in case, you know, I choose to extend the lamina and lamina includes a point P outside. Then using the same principles, I could obtain the velocity of that point P as well. Right? Now,
Toppling also be referred to as a combined.
let's go stages. Yes. Everything that I'm going to do from now on would be combined motion. Every motion is combined motion. In some cases VCM will be 0, in some cases omega will be 0, in some cases both will be 0, some cases neither will be 0. So be it toppling or anything, it will still be combined motion. So every motion is general motion. So even when we talk of toppling, that will be general motion only.
Because the engine will be at different points.
Yes. Wait for me, it will take me a long time to come to that point. I have to give you so many concepts before I embark on mission toppling, right? Otherwise, if I start talking about toppling in the true sense of the word, I'll only end up toppling you. Okay. So far so good, right? Now, so it suffices to know at any given instant of time a VCM for the rigid body, velocity of the center of mass, and the omega associated with the rigid body. And I told you how to obtain the omega. And this entire motion, like I said, could be reduced to two elementary motions, superimposition of two elementary motions, pure translation, measured by the movement of the center of mass, and then superimposed with pure rotation about the center of mass with an angular velocity omega, as if the center of mass is fixed. Right? Now, at a certain instant, let's say, at a certain instant t, let's say, this, let's say, dotted line is a line perpendicular to VCM. This is a dotted line perpendicular to VCM. And passing through the center of mass. Passing through the center of mass and perpendicular to VCM, this line. Okay. On this special line, let me look at a point P and say this point P is at a distance r from the center of mass. This point P is at a distance r from the center of mass. Now, to be able to obtain the velocity of the point P, I would superimpose pure translation with pure rotation about the center of mass with an angular velocity omega. The point P, therefore, has a velocity because of pure translation. It has a velocity VCM which it shares with the center of mass, right? Then imagine it to be fixed about the center of mass. That means as if the center of mass has no velocity, is at rest. Put it in a state of pure rotation, centered at the center of mass. Then the point P, because of pure rotation about the center of mass, would have a velocity r omega like this, would have a velocity r omega like this, perpendicular. Imagine it to be in a state of pure rotation about the center of mass. Then at this instant, because of pure rotation about the center of mass, it will move in a circle centered at the center of mass of radius r, and its velocity because of pure rotation would be r omega perpendicular to the radius. What do you say? Right? Now, for such a point P, VCM and R omega are aligned with each other. The velocity of this point P would be VCM minus R omega. If VCM is greater than R omega, P would have a velocity rightwards. If VCM is less than R omega, P would have a velocity leftwards. Right? For a certain value of R, this could also be 0. Yes or no? For a certain R, VP could be 0. Yes or no? Right? At a given instant, that is at a given instant. And for only one value of R, can VP be 0? Yes or no? Can you find more than one value of? That means there is only one point P that could be imagined that would have 0 velocity out of in this general rigid body motion scenario. There would be a unique point P whose velocity would be 0 at a given instant of time. Right? It could also be possible that this happens for a value of R such that P lies outside the rigid body. P could also lie outside the rigid body. See, like I said, the velocity field is computed notionally, as if it includes all points in the plane in which the lamina lies. Based on that presumption, the velocity is computed for every single constituent of the plane. It could even be a point outside the rigid body, but this is the consideration towards computation of the net velocity of any point P, be it actually on the rigid body or outside the rigid body. One way or the other, there would be a value of R, a unique value of R for which VP becomes 0, right? If R is large, then P would be a point outside the rigid body, else it's going to be a point on the rigid body. But uniqueness of such a point and existence of such a certain point is not under doubt. It's guaranteed, right? And such a point that has 0 velocity in general rigid body motion is called the instantaneous center, of the rigid body. P is called the instantaneous center. P is referred to as the instantaneous center of the rigid body. Henceforth, I would designate it with IC. IC, the instantaneous center, is a point whose velocity is 0. There is only one point, and there certainly is a point that has 0 velocity in general rigid body motion. It could be a point on the rigid body or it could be a point outside the rigid body. This point is referred to as the instantaneous center of the rigid body. Do you all understand this? Yes. What she's saying is, and very true, she's saying this point P will always lie on a line perpendicular to VCM. Reason being, see, this is the line perpendicular to VCM. This is the center of mass. If P was a point here, right, then this point P, let's say this is at a distance R0. Okay, then it has a velocity VCM because of pure translation. Then imagine it to be in a state of pure rotation with an angular velocity omega about the center of mass. It will move in a circle of radius R0 centered at the center of mass, and it will have a tangential velocity perpendicular to R0, which would be R0 omega like this. If P was not a point on this line, right, then the net velocity of these two vectors can never be 0. This VCM and this R0 omega can never add up to 0. Do you understand that? This would happen only if this theta was pi. This theta was pi. Which is this case?
So this also means that once the particle starts the motion, it will have to complete the circle, because
No, 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 no. The velocity of this point is 0. Its acceleration is not 0. This point has 0 velocity. If this point has 0 velocity and 0 acceleration, then it will be permanently at rest. Then it will be pure rotation about P. Then it's a hinge. Then it's a hinge.
No, but once it has started the motion,
Hmm?
then it will have to complete the circular motion, full circle.
No, 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 no. Of course not. It's the circle at that instant. It's the circle at that instant. It's a circle of radius r naught. You saying this particle has to complete r? No, not at all. Not at all. That's the whole idea. That's why we are getting very general. It will not. Okay? These are independent effects. R omega will not do anything to the center of mass because this is independent superimposition of pure translation and pure rotation. They are not interfering with each other. They can be vectorially added like this. They would have to be vectorially added like that, but they are not interfering with each other at all. Which means, you know, if I choose to give it a certain VCM and a certain omega, any pair of VCM and omega I can give it. It will not, the two will not interfere with each other. The two will only come together to determine the net velocity of any point P in the plane of the lamina. That's all. They will not interfere. They will only enable computation of the velocity of any point P if you have knowledge of these two. Now don't have to be silent again. So far so good? Is that okay so far? Right? Now, see, this is the perpendicular line. If the point P is here, no, the point P can lie. The instantaneous center cannot lie anywhere. See, instantaneous center is a point at a certain instant, the velocity of which being 0 at that instant. So P has a velocity VCM like this because of pure translation. Then imagine it to be in a state of pure rotation about the center of mass. Then it has a velocity r omega perpendicular to r naught. Now, can these two velocities add up to 0? If two velocities are not anti-parallel, can they be 0? Can the resultant of, can the length of the diagonal of this be 0? No. So then the velocity of point P cannot be 0 if it was not a point on this. It therefore cannot be the instantaneous center.
So, like physically, if it's each time it comes at P, the velocity is 0. I mean,
No, at this instant, this would be the point whose velocity is 0. At some other instance, there would be some other point whose velocity is 0. This is an irregular shape. So, you know, there would be some other point whose velocity would be 0. It would be just that it will be at a distance r. Because the point P after a while would move up. The P has 0 velocity but doesn't have 0 acceleration. Isn't it? So this point P, which you have, let's say you have marked a point P. Alright, doesn't mean that this point P will remain here. This point has 0 velocity but doesn't have 0 acceleration.
the next point that will be coming over there
Will have 0 velocity. Yes. The next point that satisfies this equal to 0 would be the instantaneous center then. So at each instant there would be a different point that would enjoy the instantaneous center status.
Suppose if there is a plate revolving, so how would there be a point which is stationary this time?
Why? Means what?
I'm having problem imagining it. Like, how is it possible?
What?
That velocity is 0.
Because of opposing effects of VCM and r omega. There is a point. There are points below the center of mass in VCM and r omega are opposing each other. What will look like? That point will look like a point. It will not look like your head. It just has 0 velocity at that instant. I mean, how can I describe how a body will look like when it is at rest? It will look like you are at rest right now. That is how it will look. It is very difficult for me to actually be in the tuned to the same wavelength, but I'm sure we are not on the same page. Huh?
How the motion will look like.
The motion will look like commensurate with VCM and omega, general motion. It will translate and reorient. Will have zero velocity but would have a tendency to move to a new position. A body released from this point. I release it. It has zero velocity but has non-zero acceleration. How will it look? How will it look, yaar? How else can I describe this? A body with zero velocity, I don't want to throw this down. Zero velocity but non-zero acceleration. Moment I release it, it will go down. Right? How will a body look like when it has zero velocity and non-zero acceleration? Tell me. No, it will not be left behind. No, it will move to a new position. A particle with zero velocity only at a given hello. A particle with zero velocity at a given instant doesn't mean that it will remain at that position at all times. It just has zero instantaneous velocity. But it has a non-zero acceleration which will move it to another position after a while.
If there's a wheel which is moving, there's a point which will remain at rest.
The point at the bottommost point of a rolling wheel will be at rest. Will be at rest at that instant of time. This is a ball, and if it is rolling, again you know, this point P will be at rest. But it will not have zero acceleration. It will have zero velocity, but will not have zero acceleration. Are you all right? Yes, now, look, so there is this concept of a point that has zero velocity in combined motion, a unique point that has zero velocity in combined motion, and we would refer to that point as the instantaneous center. Now, how good is this notion of instantaneous center? Suppose this point P is the instantaneous center of a rigid body in general motion. It has a VCM and it has an omega. This point P is the instantaneous center. Suppose this is some other particle. This is some other particle, particle 1. And its distance from the point P, the instantaneous center, is r. Its distance from the point P, the instantaneous center, is r, and this is particle 1. Right? Now, just view them separately. This is P, this is 1, this is R. P and 1 will still conform to rigid body considerations. Yes or no? What's the velocity of P? 0. What's the velocity of P in this direction? 0. If its velocity is 0, its velocity in any direction will be 0, isn't it? So what's the velocity of 1 in this direction? 0. Parallel is 0. 1 in the parallel direction is 0. Right? That means the only velocity that 1 has, it has no velocity in this direction. That means the net velocity of 1 would only be perpendicular. The net velocity of 1 would only be perpendicular, yes or no? If it was not perpendicular, then it would have a parallel component, non-zero parallel component, but that's not the case. You know what I'm saying? The net velocity of 1 would be perpendicular, because if it was not perpendicular, if it was inclined, it would have a non-zero parallel component. Got me? Right? Now, forget this for a couple of minutes. Come back to this. If I had to calculate the velocity of 1, what would I do? The center of mass, say this was R1. It will have a velocity VCM because of pure translation. It will have a velocity perpendicular to R1, which would be R1 omega because of pure rotation about the center of mass. Yes or no? Perpendicular to R1, R1 omega because of pure rotation about the center of mass. Then the net velocity of 1 would be the resultant of this VCM and R1 omega, right? Vectorially, I add this VCM and R1 omega, I end up getting the net velocity of particle 1. Is that okay? Bhai sahab, nahi samjhe? 1 because of pure translation has a velocity VCM. Huh? Imagine it to be in a state of pure rotation about the center of mass with an angular velocity omega. Then it has a velocity R1 omega perpendicular to R1. What? So the net velocity would be resultant of this VCM and R1 omega, yes or no? Huh? Okay, that's one way to calculate the velocity, isn't it? Now, look at this. P was the instantaneous center, right? It had no velocity in any direction at that instant of time. Its velocity in this direction was 0. So the velocity of had to be 0 in this direction. Why? Rigid body considerations. The net velocity of 1, therefore, the only possibility would have been, the net velocity of 1 would have been perpendicular to R, the line joining P, right? And the way to calculate omega for a rigid body is the relative. Now what's the velocity of P in this direction? 0. In this direction, 0. So to calculate the omega of the rigid body using the instantaneous center, what would I do? V1, velocity of 1 perpendicular to R, V1, which is perpendicular, divided by R, where this is the net velocity of 1. This is the net velocity of 1, yes or no? So the net velocity of 1, which is only perpendicular to this R. R is not joining the center of mass. R is joining the instantaneous center, right? V1 perpendicular, which is also the net velocity of the point 1, is R omega. Yes or no? Are you okay with this? That means if I have located the instantaneous center, then one way to directly compute the velocity of any point would be to say, well, if its distance from the instantaneous center is R, then just say R omega. That will be the net velocity of 1. Right? V1 perpendicular then simply becomes R omega. Right? And which would be the same as the velocity of 1, which is computed out of the superimposition. This is R1 omega. This is the net velocity of 1, which is the resultant of these two. And this must be equal to R omega. This must be equal to R omega. So what would you prefer if you have to calculate the velocity of 1? Would you prefer this vector addition? Or you would prefer to locate the instantaneous center first and directly obtain the velocity of any point 1? R omega perpendicular. Then no vector addition is required. right? Now, for a beginner, it might seem that, well, velocity of 1, then depending only on omega, not depending on VCM. What on earth is happening here? Why is the velocity of 1 dependent only on omega and not on VCM, whereas the velocity of any particle should be obtainable out of a blend of VCM and omega? But it seems, at least to begin with, that the velocity of 1 depends only on omega. Yes, you're right. In order to be able to locate P, I have used VCM already. Isn't it? When we located P, we said VCM minus R omega is 0, where that R was the distance from the center of mass, right? So I have used VCM to locate P, and then calculate the velocity of 1, I have used omega alone. So I have used to obtain this R, which is like distance from the instantaneous center, VCM has been deployed. VCM has been deployed, right? Only in the last lap, only in the last mile, VCM was not required because it was already consumed in the first place when we located the point P, the instantaneous center. Right? So which means now see, if this is the instantaneous center, this was particle 1, and say this distance was r, then the velocity of this point, the net velocity of this point, is perpendicular to r, which is the line joining the point with the instantaneous center, and would be r omega. Suppose there is another point 2 whose velocity I want to compute, and I have successfully located the instantaneous center at this, and this was say r prime, then the velocity of this would be perpendicular to this and would be equal to r prime omega. This would be the net velocity of 2, right? Suppose this was particle 3 and it was located at a distance r double prime from the instantaneous center, then the net velocity of 3 would be perpendicular to r double prime and would be equal to r double prime omega, and so on and so forth. Yes or no? Right. Now, at this instant, therefore, it seems like if you were an observer, the instantaneous center observer, if you were an observer, how would you perceive the motion of the rigid body? If you were an observer sitting at the instantaneous center, sharing the same kinematic status as the instantaneous center, the way you would perceive the motion of the rigid body at that instant is pure rotation. Pure rotation, different particles moving in circles of different radii centered at the instantaneous center at that instant of time. Write down, please write down. The instantaneous center observer would perceive the motion of the rigid body, to be one of pure rotation, centered at the instantaneous center, or hinged at the instantaneous center at that instant. Hinged at the instantaneous center at that instant. Right? Do you all understand this? Therefore, this makes our computation very easy. This makes our computation really, really easy. If I have located the instantaneous center, then at that instant I could imagine P to be the hinge for that instant. P to be the hinge for that instant, and I could compute the velocity of any two particles from pure rotation considerations alone. The matters get significantly simplified if we had to do that. Do you all relate to this? Right? So, two ways of looking at the motion. General rigid body motion, one, I look upon that as a combination of pure translation with pure rotation about the center of mass, or I look upon the entire motion as one being pure rotation about the instantaneous center. Either it's pure rotation about the instantaneous center which is legal, or it's the combination of pure translation with pure rotation about the center of mass. These are two independent ways of looking at the motion, and both would converge to the same net result. Both would converge to the same net result. The velocities of various particles that I have obtained using the instantaneous center ideology would be the same as the velocity obtained by superimposing pure translation with pure rotation. Do you all understand this? Now, see, if there was this rigid body in a state of pure translation, where every single particle would have a velocity equal to the velocity of the center of mass. Each particle has a velocity equal to the velocity of the center of mass. Right? Let's say this is the ith particle having mass mi. Various mi's constitute the rigid body. Various mi's constitute the rigid body. The total kinetic energy of the rigid body would be the sum of the kinetic energies of the various mi's. Right? So this mi has kinetic energy half mi. VCm squared is the kinetic energy of this ith particle. The total kinetic energy of the rigid body would be the sum of all of this computed over various i's. Right? But since it's a state of pure translation, VCm is independent of I, and therefore it can break free from the summation sign. It can break free from the summation sign. So this would be the same as summation half can come out. Mi can stay inside the summation, and VCm squared can break free from the summation sign. Sigma mi is the total mass of the rigid body. Sigma mi would be the total mass of the rigid body, and the kinetic energy then would be deemed half m VCm squared. What do you say? Right? So that's the kinetic energy in pure translation, half m into square of the velocity of the center of mass. Now, say pure rotation. Hinged at edge. Hinged at edge. In pure rotation, there would be a point permanently at rest. In general motion, there would be a point only at rest at that instant. It will not be permanently at rest. There would be a point which is at rest at that instant, and therefore the entire body could be imagined to be in a state of pure rotation about that point for that instant. So it's a hinge for that instant. In pure rotation, it's the same hinge at all instants. In pure rotation, it's the same hinge at all instants. That's the difference. Okay. So this rigid body in a state of pure rotation about h, this is the axis of rotation. Okay, this is omega. Angular velocity will uniquely determine the velocity of all points constituting the rigid body. Every point will move in a circle centered at h and in general of different radii ri. So if this is a particle I, at a distance ri from the axis, right? This is the axis of rotation. So this is at a distance ri from the axis of rotation. So it has a velocity vi, which is ri omega. Velocity vi, which is ri omega. This is of mass mi. This particle I is of mass mi, right? Now, the kinetic energy associated with this, I hope you realize this ri omega would be perpendicular to ri. It's moving in a circle centered at h and of radius ri, right? The kinetic energy associated with the ith particle would be half of mi into vi squared, which is ri squared into omega squared. The total kinetic energy would be, sum of all of this would be the total kinetic energy of the rigid body in pure rotation. Yes or no? Right? Now, since it's a state of pure rotation, this omega will be the same for all I. So again, it will cut loose out of the summation sign, right? So it scoops out of the summation sign. Half also scoops out of the summation sign. Only the I entities stay within to get summed up with omega squared neatly outside, right? Now this entity summation mi squared, which is obtained by taking any mass, square of its distance from the axis of rotation, right? Another mass, square of its distance from the axis of rotation. I add up this mi squared for various particles. The value of this will depend on the various ri's. That means how the mi's are distributed about the hinge edge. That is, how the various mi's are distributed about the axis of rotation. Yes or no? So this depends on the mass distribution about the axis of rotation. This quantity depends on how the mass is distributed. Mass elements are distributed about the axis of rotation passing through H. This quantity will depend on that, right? It has nothing to do with omega or other things, right? It only depends on where the axis of rotation is, and therefore distribution of mass elements about the axis of rotation. Therefore this would be a computation that would have to be made in order to calculate the kinetic energy in pure rotation. This calculation would have to be made. What we do is we create standardized templates for this computation. We give it a certain name. We call this computation summation mi squared as the moment of inertia about the axis of rotation. This summation mi squared is the moment of inertia about the axis of rotation. IAOR is axis of rotation. And we commonly designate it as, say, I about an axis passing through H. I about an axis passing through H and perpendicular to the plane of the lamina. In this case, perpendicular to the plane of the lamina. Right? That's moment of inertia about an axis passing through H and perpendicular to the plane of the lamina. Do you understand this? Is the idea clear? Now, so kinetic energy in pure rotation can be obtained as half of I about H, an axis passing through H, into square of omega. That's the kinetic energy in pure rotation. Right? Now, kinetic energy in general rigid body motion. Kinetic energy in general rigid body motion. Let's examine that. Fundamentals will remain the same. We would have just different cosmetic looks emerging out of general rigid body motion, right? I will still have to look at the kinetic energy of every particle and add it up. Right? That's what we would need to do. Yes. If these Ri's are more, if the particles are spread out further from the axis of rotation, this will have a greater value. Therefore, if spread out further from the axis of rotation, then this would be a greater number, and for the same omega, you will have greater kinetic energy. Yes. Now, general rigid body motion. How to obtain the kinetic energy in general rigid body motion. Okay. So, general rigid body motion comprehensively characterized by two things. A VCM and omega. A VCM and omega would determine general rigid body motion comprehensively. Clear? Say there is a particle P here of mass Mi, and it's at a distance Ri. Okay. Right. Its velocity is going to be, because of pure rotation, pure translation, it will share a velocity VCM like this with the center of mass, right? It will also have a velocity perpendicular to Ri, Ri omega like this, right? Now, suppose this angle is theta, this will also be theta. Or what we might do is angle, since we'll vectorially add these two velocities, might as well call this theta. Might as well call this theta. Okay. This will then be 90 minus theta, and this will be theta. Right? So far so good? Now how to obtain the kinetic energy of Mi? First of all, I would need to obtain the velocity of Mi. For this particle Mi, there is a VCM like this, there is a RI omega like this, there is theta like this. Then from parallelogram law of vectors, I would obtain the velocity Vi of this particle, right? What would be Vi squared? VCM squared plus Ri omega squared plus 2 VCM Ri omega cos theta, right? Right? Now, suppose this was the x-axis and say this was the origin, center of mass let me choose as the origin, and say this was the y-axis, say. This was the y-axis. Alright, center of mass, the origin, say this was the x-axis and this was the y-axis. Clear? Now, the kinetic energy of the ith particle would be half of mi Vi squared. Yes or no? The total kinetic energy of the rigid body would be a summation carried out over these half of mi Vi squares. Which would be half of summation mi. Now this Vi squared I can write as this. Now also realize that this Ri cos theta, this is Ri. Ri cos theta would be the y coordinate of the point P. Yes or no? This is Ri. This is the center of mass. This is theta. This is the point P. The point P has x coordinate xi and y coordinate yi. Right? Then Ri cos theta is really the y coordinate of the point P. Ri cos theta is really the y coordinate of the point P. Yes or no? Ri cos theta, y coordinate of the point P. Is that okay? So now this Ri cos theta I can write as yi. I can write as yi. Shall I do it right here? So this is VCM yi omega, that Ri cos theta replaced by yi. Now mi Vi squared, half of mi summation mi Vi squared. Vi squared is VCM squared plus Ri squared omega squared, right? Ri squared omega squared plus twice VCM omega yi. Yes or no? Which is like half of summation mi VCM squared plus half of summation mi Ri squared into omega squared. Yes or no? The second term plus this 2 will get cancelled with this 2. Summation mi VCM omega yi. Yes or no? In this case, VCM is independent of I. It will come out and summation mi would be the total mass. See, summation mi would be the total mass of the rigid body. So this then becomes half of m VCM squared, right? Now omega is independent of I, so omega squared can come out. So if omega squared comes out, then summation mi Ri squared is what you are left with. That is ICM. Summation mi ri squared is I about an axis passing through the center of mass. Yes or no? Right? So then this becomes half of, this becomes ICM. Axis of rotation, moment of inertia about an axis passing through the center of mass, because these I's, RI's are measured with respect to the center of mass. Right? Half of ICM, I about the center of mass, into omega squared. Now, in this case, VCM and omega will scoop out. They are independent of I. So, VCM omega summation MIYI absolutely summation MIYI by summation MI will give me the y coordinate of the center of mass, yes or no? Which is 0, because the center of mass is the origin. Therefore, summation MIYI is 0. Summation MIYI is 0. So this is rendered 0. Summation MIYI is 0. Okay, what's the y coordinate of the center of mass? Summation MIYI by summation MI? But the center of mass is the origin. So YCM is 0. Therefore, summation MI YI is 0 into summation MI, which is 0.00. Right? No? Are you still confused? Diptesh, I mean, sure though. So, which is like half of MVCM squared plus half of ICM omega squared. That's a kinetic energy.
But then this will only hold valid when YCM is 0. Like then the YCM term will.
No, then everything will change. Arey Baba, these physical facts will not change. It's not like if kinetic energy I have got as this by choosing the center of mass as the origin, then if I didn't choose the center of mass as the origin, will the kinetic energy of the rigid body change? The kinetic energy will still be the same, isn't it? So, physical facts don't change because of choice of origin or choice of coordinate axis. Please ask. Yes, I'm coming to that also. Yes, that's exactly the next that I'm going to tell you. But this is fine, right? Now, so the way you could interpret this and at least remember this, can I wipe this off? See, it's as if, you know, this motion, combined motion, characterized by VCM and omega, looked upon as pure translation, VCM plus pure rotation about center of mass. It's as if this is hinged and it has an angular velocity omega. It's the result could be looked upon as the contribution made by this, which is half m VCM squared, and in a state of pure rotation about the center of mass with angular velocity omega, the kinetic energy, like I said, in pure rotation is going to be I about the hinge into omega squared. That's the way you could remember this or interpret this. This is because of pure translation. This is because of pure rotation. Is that all right or not all right? Now, coming to your issue now. Can I wipe this off? We could have, instead of superimposing two elementary motions, I could have perceived this entire motion. I could have perceived this entire motion to be, suppose P is the instantaneous center, which is located with the aid of VCM and omega both together would connive to locate the instantaneous center. So used up to obtain P. I could imagine this to be hinged about P and to be in a state of pure rotation about the instantaneous center, right? To be in a state of pure rotation with an angular velocity omega about the instantaneous center, yes or no, right? And suppose these RIs are distances measured not from the center of mass but from the instantaneous center, then the velocity, let's say, of a particle I with mass mi is going to be Ri omega perpendicular to this. The kinetic energy then, right, and the same velocity could have been obtained by superimposing pure translation with pure rotation. So the kinetic energy then is like half of mi into vi squared. Summation of this will give me the total kinetic energy of the rigid body, which is half of summation mi into vi squared. Vi squared is Ri squared omega squared. Ri squared omega squared, where these Ri's are measured not from the center of mass but from the instantaneous center. Right? Vi is Ri omega, so Ri squared omega squared. Omega squared would come out. It's independent of I. So this is half of summation mi squared into omega squared. What is this? I about the instantaneous center P. This is I about the instantaneous center P. I about the instantaneous center P into omega squared. IP is moment of inertia about the instantaneous center P, about an axis passing through the instantaneous center P. Which is what you expected, because the whole body was in a state of pure rotation about the instantaneous center, and in pure rotation the format of kinetic energy would look like this. And the same kinetic energy could also have been obtained by using the expression half m VCM squared plus half I CM into omega squared. Right? Moment of inertia computation then. Okay, since this is going to be a tool that we are going to use across the various layers of rotational mechanics, so let's understand this tool properly right away. Okay, so like I told you, if this is a rigid body and there is an axis passing through a point O and say perpendicular to the plane of this body, and there is a mass mi at a distance Ri from this axis, right? Then for every particle we do this calculation mi Ri squared and do a summation, and that's going to give me moment of inertia about an axis perpendicular and passing through O, right? That's the way we do a basic moment of inertia calculation. So in the event it's not a discrete collection of particles, this summation would be replaced by an integration. That's all that would be required, right? Let me first of all and right away give you moment of inertia computation for some very regular geometries, right? So, and then move on to some more sophisticated tools. So, first of all, let's look at moment of inertia computation for a ring or a circular arc, say, a circular arc. of radius r and mass m. Circular arc of radius r and mass m. Okay. This is a circular arc PQ, centered at O and radius r. Right? We want to be able to do a moment of inertia calculation for this circular arc about an axis passing through O and perpendicular to the plane of the arc. Perpendicular to the plane of the arc, passing through O, I want to be able to do the moment of inertia calculation. Right? What we do is, we break this arc into small mass elements. We find the distance from O, and therefore the distance from the axis, do a mi/ri squared for every mass and carry out a conventional summation, right? So I take a mass element, let's say dm, and this being the axis, the distance of this mass element from dm is r. Its moment of inertia contribution about O, its moment of inertia contribution about O, di of the mass element is going to be dm into r squared, dm into r squared, right? The total moment of then would be sum of all these di's taken for all the dm's starting from p to q, right? So the total moment of inertia would be sum of all these r square dm's, computed this integration or this summation carried out over the circular arc for all mass elements constituting the circular arc, right? Now r square is the same for all the dm's that you select, right? So the r squared would come out of the integral sign. So r squared, and then integral dm means sum of all the mass elements. Sum of the mass elements is going to be capital M, the mass. So that's going to be mr squared about an axis passing through the center of the ring and perpendicular to the plane of the ring, right? That's mr squared. And it does not depend on theta, the angle that it subtends at the center. It does not depend on theta. So if theta was 2 pi, it will be same, right? So if I had a circular ring, if I had a circular ring of mass m and radius r, the only difference between this and this is theta becomes 2 pi for this. Theta is rendered 2 pi for this. So the moment of inertia about an axis passing through O and perpendicular to the plane of the ring will still be mr squared. So the moment of inertia about an axis passing through O perpendicular to the plane of the ring is going to be mr squared. Yes or no? Right? It's not an indefinite integral. Reason I'm not supplying the limits is that, you know, there is no need. I have to notionally judge what this means. It means sum of all the dm's. Take the dm here. I mean, if you want to just put, you can say dm starting from p all the way to q, just to be notionally right, right? It means take all the dm's from p to q and add them up. That'll give you the total mass element. It is definite, but then it's unnecessary to invoke limits here. Okay? Is that okay or not? Right? So whether it's a circular arc or a circular ring of mass m and radius r, the moment of inertia about an axis passing through O and perpendicular to the plane is going to be mr squared. What if this ring is non-uniform? What will be the moment of inertia about an axis passing through O? It's going to be the same, because it's going to be the same, because see, in this integral dm will be the total mass. It does not matter whether this mass is heavier, with this dm is heavier than this dm. Sum of all the dm's will still be m, right? So this result, moment of inertia about an axis passing through O perpendicular to the plane of the ring, is mr squared, true irrespective of whether the ring is homogeneous or non-homogeneous. Got me? True both for homogeneous, uniform as well as non-uniform arrangement of mass elements on the ring. Clear? Now, Now, instead of the ring, suppose we had a disk, right? Mass m, radius r. Say uniform disk with mass per unit area sigma m divided by pi r squared is the mass per unit area of the disk. Clear? Disk means it's this. This is, and I'm talking of a uniform disk. Right? This is a disk. What I do is, a disk could be imagined to be composed of infinite rings. This is one constituent of the disk. Several such concentric rings of different radii, starting from radius small r, starting from r equal to 0 to r equal to capital R. This is a chosen ring of radius small r and of thickness dr. Right? This entire disk could be imagined to be composed of infinite number of such concentric rings, starting from r equal to 0 to r equal to capital R, will constitute the disk. Right? If I superimpose these rings, then the disk will be produced. Isn't it? Yes or no? Now, so I want to be able to compute the moment of inertia about an axis passing through O and perpendicular to the plane of the disk. So let me look at the contribution made by this chosen ring. First of all, what's the mass of this ring? Mass of this ring is sigma into, this is mass per unit area into the area of the ring. Sigma is mass per unit area, isn't it? Into the area of the ring. Area of the ring is circumference into thickness would be the area of the shaded portion, isn't it? Circumference is 2 pi r into dr would be the area of the ring. Mass per unit area into area. Right? That's the mass of the ring. But the moment of inertia that this contributes is mass into small r squared is the moment of inertia of the ring. Yes or no? So this into r squared, this is the mass into r squared, that would be the moment of inertia contribution made by the ring about an axis passing through O and perpendicular to the plane. Right? The total moment of inertia would be sum of the contribution made by all the rings, starting from r equal to 0 to r equal to capital R. That's the moment of inertia about an axis passing through O and perpendicular to the plane of the disk. Right? Now what you do is, this sigma you can replace by m by pi r squared. Right? This sigma you can replace by m by pi r squared. This pi will get cancelled. R cube, when you integrate, you will get r to power 4 by 4. Right? And this will give you half mr squared. You can check that out. Half mr squared is what you'll get as moment of inertia about an axis passing through the plane of the disk, perpendicular and passing through O and perpendicular to the plane of the disk. Right? Half mr squared. Half mr squared. Clear? Now, I'll now compute the moment of inertia of a sector. Okay. Sector of a disk. I have computed for sector of a ring. Now I'll take sector of a disk. So far so good. Yes or no? Right. This is a sector. By the way, in this case, the disk has to be uniform, half mr squared, because this sigma, I've assumed constant m by pi r squared. That means mass per unit area is the same at every point of the disk. So uniformity of the disk is a necessity in order that I could use the result half mr squared as moment of inertia about an axis as shown. Right? Now, a sector of a disk. Mass m and radius r. say an angle theta at the center. Clear? I want to compute the moment of inertia about an axis passing through O and perpendicular to the plane of the sector, right? What we do here essentially is realize that n such sectors will make a full disk, right? And so on and so forth. That means n theta is 2 pi. N sectors will make a full disk. See, this is one sector, this is another sector, another sector, another sector. I imagine a disk with n such sectors, right? N sectors. And I create a full disk. I take n such sectors and I create a full disk. How can I create n such sectors? If n is chosen such that n theta is 2 pi. Clear? Now, n such sectors means that the total mass now of this area that I am imagining is n into m, because each sector would be of mass m. Yes or no? Each sector would be of mass m, right? The moment of inertia of this disk would be the moment of inertia of this, plus this, plus this, plus this, plus this, plus this, etc. And the moment of inertia of each of these is the same. Yes or no? About O. About an axis passing through O and perpendicular to the disk. Isn't it? So if I is the moment of inertia of each sector, then the total moment of inertia of this is going to be n times I naught. Yes or no? If I naught is the moment of inertia of this about an axis passing through O and perpendicular to the plane, then the total moment of inertia of this is going to be n times I naught. Yes or no? Yes, right? Which is a full disk. For a full disk, half of the total mass into square of the radius. Right. Half of the total mass of the disk is going to be nm into r squared. Nm into r squared. Yes or no? Do you all understand this? Right? So then I naught still turns out to be half mr squared. Clear? Now, simple, right? Yes, thank you. Suppose there is a thin uniform rod mass m, length L. Mass m, length L. Thin uniform rod, mass m and length L. Clear? Now, this is the rod, say thin rod PQ of length L. Uniform and of length L. This is an axis passing through the center of mass of the rod. Suppose the center of mass is the origin, and let's say this is the x direction. Then Q would have x equal to L by 2, P would have x equal to minus L by 2. Yes or no? I want to be able to compute the moment of inertia about an axis passing through the center of mass. AA is an axis passing through the center of mass and perpendicular to the rod. Perpendicular to the rod, right? See, a thin rod doesn't determine a plane. If this is a thin rod, then the plane could be like this, the plane could be like this, the plane could be like this. Yes or no? Containing a line, you can have infinite planes. So we don't talk of a plane, it's just perpendicular to the rod. About any axis perpendicular to the plane of perpendicular to the rod and passing through its center of mass. I want to be able to compute the moment of inertia. Right? What I do is I take a mass element here. This is a small mass element chosen at a distance x and of length dx. This is a mass element chosen, right? Now the moment of inertia contribution of this mass element is going to be, first of mass of dx is going to be, well, mass per unit length is m by l into dx is the mass of this dx, isn't it? The moment of inertia contribution about this axis is going to be into x squared. The total moment of inertia about this axis AA is going to be sum of all of this, where x runs from minus L by 2 to plus L by 2. That's the moment of inertia about an axis passing through the center of mass and perpendicular to the rod. Yes or no? When you integrate this, this would be x cubed by 3. When you integrate this, the result will turn out to be 1/12 ml squared. 1/12 ml squared. Got me? Now, can I wipe this off? Can I wipe this off? Huh? Then it will not be the same, necessarily be the same. It could be equal mass on both sides, but it could still be non-uniform, equal distribution on both sides, right? It will not be this. Now, suppose we had two discrete masses, 2 point particles m1 and m2, 2 point particles separated by a distance r. 2 point particles separated by a distance r. Separated by a distance r. Now together they have a center of mass which is at a distance r1 from m1 and r2 from m2, which is at a distance r1 from m1 and r2 from m2. Now if you remember, I am not sure if you remember, but r1 is m1r m2r divided by m1 plus m2. Remember this? R2 is m1r divided by m1 plus m2. Now suppose this is an axis perpendicular to the line joining the two particles. This is an axis perpendicular to the line joining the two particles, and I want to be able to compute the moment of inertia about AA for this pair of particles, right? I about an axis perpendicular to the line joining the two and passing through the center of mass. What is it going to be? m1 r1 squared, the contribution made by this, plus m2 r2 squared, the contribution made by the other one, right? Yes or no? Which is going to be m1 r1 squared. R1 squared is square of this. Whole square, right? Now this could be looked upon as m1 m2 by m1 plus m2. I take m1 m2 common, and within the parenthesis I am left with m1 plus m2 into r squared is what resides, right? So which is like m1 m2 divided by m1 plus m2 into r squared But m1 m2 by m1 plus m2 is the reduced mass, mu. So this is mu, the reduced mass. Mu, reduced mass for the pair. So it turns out to be mu r squared. R is the separation between the two particles. R is the separation between the two particles. Sounds all right? Hmm? Now, so far so good, na? Confused kya? Confused? No? This is how some basic computations are made. You can use these first principles to carry out a computation of any geometry about any axis. Okay, but two results related to moment of inertia would come in very handy in certain situations, would significantly reduce the rigor of computation. One is suppose this is a rigid body, right? And this is the center of mass. This is an axis AA passing through the center of mass. This is another axis, say BB, parallel to the center of mass axis. Axis center of mass axis. This is an axis parallel to the center of mass axis, right? And say the separation between them is D. There are times you would know I about this CM axis and you would want to calculate I about an axis parallel to the center of mass axis, right? Now what we do is, suppose there is a particle mass mi at a distance ri from this axis. Then its distance from this axis is going to be d minus Ri. Yes or no? It's going to be d minus Ri. Right? Yes. It's going to be d minus Ri. And let me call this, suppose center of mass is the origin. Suppose the center of mass is the origin. Clear? Then the moment of inertia about BB is going to be what? Summation mi d minus Ri whole square. Summation mi into d minus I, right? Mass of the element into square of its distance from BB. Summation of this will give you moment of inertia about BB, right? Right? Which is going to be summation mi d squared minus twice mi Ri d plus Ri squared. Summation of this mi Ri squared. Right? This is like summation mi d squared minus, now d can come out of the summation because d is a constant, separation between the two parallel axes, right? Twice d summation mi Ri plus summation mi Ri squared. Yes or no? Now realize that if I have to do a summation mi Ri, then summation mi Ri by summation mi would actually give me r of the center of mass, 0, which is 0. Yes or no? That means summation mi Ri is 0. So then this makes, and this summation mi, see this d squared can come out of the summation sign, and summation mi is going to be the total mass of the rigid body. So then this is going to be md squared.
plus IA.
This will become 0. And this is I about an axis passing through the center of mass, right? So this is going to be ICM. Right, so this gives me parallel axis theorem. I about an axis parallel to the center of mass axis is going to be I about the center of mass axis, m into d squared. That's the parallel axis theorem. Parallel axis theorem. It's not like I about one axis would be I about any other axis plus md squared. It'll be I about an axis. The other one has to be the center of mass axis. Parallel but center of mass axis. Because if it was not the center of mass axis, then this summation MIRI will not be 0. Right? Then this result will not hold good. If this was not the center of mass axis, then this result will not hold good. Right? Don't say that I2 is I1 plus md squared, where the separation between 1 and 2 is d. No. I1 must be the center of mass axis, or ICM. Clear? The other result very commonly used is what's popularly known as the perpendicular axis theorem. Perpendicular axis theorem. Suppose this was a rigid body. And say this rigid body was laminar rigid body. What this result is going to be about a laminar rigid body. This result is going to be about a plain laminar body. Laminar rigid body. This is the body lies in the xy plane. This body lies in the xy plane. The lamina lies in the xy plane. Right? And the z axis is perpendicular to the lamina. Z axis is perpendicular to the lamina. Clear? Now, suppose I take a point P. A mass element here at P, mass element Mi, and say P is at xi yi. The coordinates of P is xi yi. Now, this is x, this is y. Perpendicular. This length would be yi, this length would be xi. Yes or no? If this point is O. And this O need not be the center of mass. By the way, this O need not be the center of mass. Okay. Do you understand what I've done there? Right? Now, the moment of inertia about the x-axis, right? Suppose the mass element is Mi, then the moment of inertia about the x-axis is going to be summation Mi yi squared, square of its distance from the x-axis, right? Summation Mi yi squared would be the moment of inertia about the x-axis, right? Moment of inertia about the y-axis is going to be summation Mi. Distance from the y-axis is xi, so summation Mi xi squared. Yes or no?
Yes, sir.
Now, do you also realize that for this point P, this is the z direction, its distance from the z-axis is r? Its distance from the z-axis is r, yes or no? Distance of this point from the z-axis is r, where r squared, or let's say ri squared is xi squared plus yi squared. is xi squared plus yi squared is ri squared. Clear? So if I have to calculate I about the z axis, then I'll do a summation mi ri squared, then I'll do a summation mi ri squared. So I about the z axis is going to be summation mi ri squared, right? Summation ri squared means summation mi xi squared plus yi squared, summation mi xi squared plus yi squared, but that's like summation mi xi squared plus summation mi yi squared, yes or no? So this is like a I xx plus I yy. Got me? So moment of inertia about an axis perpendicular to the plane of the lamina would be the sum of the moment of inertia about the two axes in the lamina, x and the y axis, say in the plane of the lamina. That's the perpendicular axis theorem, right? Let's get quickly into the applications of these two results. So far so good, right? Now let's look at the ring. Let's look at the ring. This is a ring, mass m and radius r. Mass m and radius r. This time a uniform ring. Right? This is O. We have calculated I about O as mr squared, isn't it? I about an axis perpendicular to the ring passing through its center is mr squared, right? I about O. I about an axis passing through the center and perpendicular to the ring, plane of the ring is mr squared, right? Now I want to calculate I about a diameter. This is a diameter PP. PP is a diameter. I want to be able to calculate I about a diameter. I about PP. PP is a certain diameter. Clear? I about this axis I know. Coming out of the plane, let's say perpendicular to the plane, passing through the center is mr squared. I want to calculate I about PP. Yes or no? Prakhar, you look zombied. No? You're doing good? Feeling normal? Wow. Now, I take another diameter perpendicular. Any other diameter, but this time I take a diameter, another diameter which is perpendicular to PP. QQ, right? Would you mind believing that I about PP will be the same as I about QQ because of symmetry? Yes. Because of symmetry, I about PP will be the same as I about QQ, provided the ring is uniform. This time the ring has to be uniform. For mr squared, this need not be uniform, but in order that moment of inertia about this diameter is the same as moment of inertia about this diameter, it has to observe symmetry. It has to maintain symmetry, right? So then if it's, that's why I said a uniform ring this time. In the earlier case, I said no, it's not required to be uniform for this calculation, right? So I about PP is the same as I about QQ. If the ring is uniform, these are just two diameters and they would produce the same moment of inertia. Clear? Now, from perpendicular axis theorem, this is an axis, this is another axis, and IO is perpendicular to PP and QQ. This is the Z direction. This is the X direction, say this is the Y direction, then this will be the Z direction. Then from perpendicular axis theorem, can I say I about the perpendicular direction, perpendicular to the plane, is going to be I about PP plus I about QQ. Can this be said? But they are equal from symmetry. So this is twice I about PP. Yes or no? So I about PP is going to be half of I naught. Half of I naught means half of mr squared. So I about a diameter of a ring is going to be half mr squared about a diameter. Suppose now, and this is a diameter, of course, needless to say, it passes through the center of mass of the ring. Now suppose I want to calculate I about tt, where tt is at a distance d from pp. Then I'll deploy parallel axis theorem. So I about tt is going to be I about parallel axis passing through the center of mass plus md squared. So that's going to be I about pp plus md squared. I about pp is half mr squared plus md squared. If tt is a tangent, then this d will be r. If tt is a tangent, then this d will be r. And this will become 3 by 2 mr squared about a tangent. Clear? Is that all right? Suppose, stay put now please. This is a ring, uniform ring, mass m and radius r. Mass m and radius r. And I want to be able to calculate moment of inertia about an axis pp, which is a diameter, about a diametrical axis, I want to calculate moment of inertia. I know the moment of inertia about this half mr squared, perpendicular to the plane and passing through the center of mass. That's half mr squared, yes or no? Yes, I about this, right? Sorry, disk. Oh, so sorry. I have. Sorry. Disk. I is half mr square.
Yes, sir.
Right? Now, if I take two perpendicular diameters, PP and QQ, then do you realize IPP will be the same as IQQ? But IPP plus IQQ would be this I from perpendicular axis theorem. IPP will be equal to IQQ, and IPP plus IQQ would be I half mr squared from perpendicular axis theorem. Yes or no? Yes, sir. Right. So IPP plus IQQ is I, which is half mr squared. So IPP, any diameter, would be 1/4 mr squared. Sounds all right? And of course, now if you know IPP, you could suppose this was some TT, then I about TT you can deploy parallel axis theorem. If this was D, then I about TT would be I about PP plus MD squared, isn't it? I about TT is going to be I about a center of mass axis, parallel center of mass axis plus MD squared.
Yes, sir.
So what does moment of inertia physically represent?
Mass distribution used towards computation of kinetic energy, let's say, to begin with. So we encountered an entity summation mi ri squared, and we wanted to give it a name. A new child was born and we gave it a name. That's what and physically its value will depend on how mass is distributed with respect to an axis. That's what it physically represents, right? Clear? Suppose there was a uniform circular disk. of mass m and radius r. Uniform circular disk of mass m and radius r. O is the center of the disk, say. O is the center of the disk. Right? This was the disk. Yes, everything about the disk is uniform. And when the ring comes, except IO, when we said I about PP is the same as I about QQ, then what was required was uniformity. Otherwise, the two diameters would be treated differently. Right? Now, say this was the disk. And what I did out of the disk was, I scooped out some material from the disk. Say, I scooped out a smaller disk of radius r by 2. C was the center of this. I removed this portion. I removed this portion. If this was of radius r by 2, then this disk will pass through O, isn't it? This disk will pass through O. If m was the mass of this, then what I removed was mass m by 4, yes or no? Because the radius of the area of this is 1/4 the area of this whole thing. Therefore, the mass of the removed portion would be 1/4 the total mass. Clear? Right? So, m by 4 was scooped out. I now want I about O. For this revised geometry, I want to be able to calculate I about O. So what I essentially have to do is, the new I about O, revised, I about O previous, let me call this I about O previous, I prime O, right? That is this. Minus, I want to remove the contribution of this about O, minus I of the removed portion, I of the removed portion about O, minus I of the removed portion about O. That's what I want to do. I of this minus I of this smaller disk about O. That's what I want to do, right? Yes, sir. Okay. Now this I previous would be half mr squared, right? This quantity is going to be half mr squared. Okay. Minus I of this about O. So what I'll take I of this about this axis, and then to calculate I about this axis, I'll have to deploy parallel axis theorem. What's the I of this about C? Half of mass of this is m by 4 into r by 2 squared. That's I about C. That's I about C, isn't it? Half of the mass of the removed portion into square of its radius, plus m by 4 into r by 2 squared. This d is r by 2, so plus m by 4 into r by 2 squared. That's going to give me I about O for this disk. So I have removed from the original one the I about O. What this contributed about O, I have removed. The smaller disk had this kind of a contribution about O. Do you all understand this? Then that will give me I about. No problem. See, this IO is half mr squared. Now once I remove this, then I have the shaded portion left. So I now want to calculate the I about O for this revised geometry. So what I need to do is, the original I about O, from that I will have to remove the contribution made by this. The original I about O was half mr squared. Now I want to remove from that the contribution made by the smaller disk about O. Now the smaller disk, I know I about C. What is it? Half of mass of the disk into square of its radius is I about its center, right? But I want to know I about O. So I'll have to apply parallel axis theorem. So half of mr squared plus m into d squared. M of this is m by 4, d is r by 2. So that I get I about O for this removed portion. This is I about C for the removed portion, but I need I about O for the removed portion. Clear? So I'll have to deploy parallel axis theorem. Clear? I don't bother about that. You can add, subtract, multiply, divide. I know that. Now, for this rod, uniform rod PQ, mass M and length L. Mass M and length L. Right? If this was the center of mass of this uniform rod, then do you remember? I about this center of mass axis is 1/12 ml squared. Is 1/12 ml squared? If I want to calculate the I about one end of the rod and perpendicular to the rod, then realize in this case this d is L by 2. To calculate I about this axis, say axis AA, I'll have to deploy parallel axis theorem. So I about AA is going to be ICM, which is 1/12 ml squared plus m into L by 2 squared, right? This is 1/3 ml squared about an axis perpendicular to the rod and passing through one end is going to be 1/3 ml squared. Suppose I want to calculate for a rod I about an axis which is not perpendicular to the rod, passing through one end but inclined to the rod, inclined at an angle non 90 degrees with the rod. Okay, so far so good. Yes or no? And what would be I of PQ about an axis passing through PQ? 0. See, if this was a rod PQ, tell me what is I about PQ? Yes, all mass elements R will be 0. So I about its own length is going to be 0 always. Clear? Suppose now we had say if this was a rod PQ and I want to calculate I about this axis AA. I about this axis which is not perpendicular to the rod, right? I want to be able to calculate I about this axis, right? Now what we do is I take a mass element here, right? I take a mass element here which is at a distance x from the end P. That means this is an axis perpendicular to PQ. This is an axis perpendicular to PQ. This one, the one that the pen shows, is perpendicular to PQ, right? Yes or no? This is inclined to PQ, right? And say this mass element was dm. Now what is this distance? Distance from AA is going to be x sine theta, right? So I about AA is going to be sum of all the dm's into x sine theta whole squared. Yes or no? This is the square of the distance from AA?
Yes, sir.
No? Right? Now sine square theta would be the same for all the dm's. So sine square theta will come out. So this then is written as x squared dm into sine square theta, right? But dm into x squared, see, all these x's are distances from an axis perpendicular to PQ. So do you realize that this will be 1/3 ml squared? Moment of inertia about an axis perpendicular to the rod and passing through one end is going to be computed. Say if this was the axis, how would you compute the moment of inertia about this axis? 1/3 ml squared, right? So, and for that you will have to use x as these distances. So dm into x squares will give me 1/3 ml squared, right? So this would be like 1/3 ml squared into sine square theta, right? Suppose we had the following. Say if this was AB was a rod of mass m and length L. AB was a rod of mass m and length L. Clear? And AC was also a rod of mass m and length L. And I want to calculate I about an axis passing through B and perpendicular to the plane of the L. You know what I am saying? I want to be able to calculate I about an axis passing through B and perpendicular to the plane. I want to be able to calculate I about an axis passing through B and perpendicular to the plane of the L. This is an L-shaped structure. Word, right? So I'll have to take I about B of AB and then I about B AC. Yes or no?
Yes, sir.
In order to calculate the total moment of inertia about B, I'll have to find out the contribution made by this about this axis, which is going to be 1/3 ml squared, and contribution made by this about this axis. Yes or no? Now realize, hey, what we'll have to do here is, this is the center of mass of AC. I about this axis is 1/12 ml squared. I about this axis is 1/3 ml squared, right? Now what I need is I about this axis of this. So then the distance d between the two axes will be this d. Yes or no? This length is L. This length is going to be L by 2. Right? So the distance between the two parallel axes, this axis and this axis, is this d, which can be computed out of Pythagoras theorem. So this is root L squared plus L squared by 4, which is root 5L by 2, which is root 5L by 2. Yes or no? Yes. Right? So then we are all set, right? The contribution made by this about this axis is going to be 1/12 ml squared, which is about this, plus m into d squared, right? Plus m into d squared. D squared is 5L squared by 4, and I of AB about this is 1/3 ml squared. That's going to be the required I about an axis passing through B and perpendicular to the plane of the L. Clear? No, sorry, I just missed out on everything that you said. Moment of inertia along AB of what? Along AC of AC along AB. Okay, so which means about this axis, huh? Then we'll have to take, like, each of these I'll have to take the distance. So m into L squared. No, I'll have to take a mass element here, right, into square of its distance from this, mass element here, square of its distance from this. So about AB, it's going to be 1/3 ml squared only. Then AB along AC. What will that do?
So,
Perpendicular axis theorem.
so she's saying to find along A and then along B, but that's not possible.
No, you can't translate this to this, because this is not the center of mass. That's precisely the reason I had this choice of center of mass. I can't say I about B would be I about A plus ml squared. No, never. Because one of them has to be the center of mass for parallel axis theorem. Perpendicular axis theorem, it need not be the center of mass, but for parallel axis theorem, one must be the center of mass, right? Square uniform plate, okay. Uniform square lamina. Let's say of dimensions A by B. Of dimensions A by B. Uniform square lamina of dimensions A by B. Let's don't get petty about all this. So m by AB is the mass per unit area. M by AB is the mass per unit area of this lamina, which is a fact that we are going to use. Mass per unit area is m by AB. I want to calculate, this is the center of mass. I want to be able to calculate about this axis AA. About this axis AA, I want to be able to calculate the moment of inertia of this square lamina. I mean, this is like this particles everywhere, right? What I do is I choose a mass, a strip like this, right, at a distance x from AA and of thickness dx, right? Then what's the mass of this element? What's the area of this element? B into dx. B into dx is the area of this element. Into mass per unit area will give me the mass of this element. Into x squared will give me the moment of inertia contribution made by this element, because every point on this is at a distance x. So mass into x squared would give me the moment of inertia that this chosen strip contributes about AA. So into x squared, right? Suppose this is the origin and say this is the x direction, integrated starting from this would be x equal to minus a by 2 and this would be x equal to a by 2. Yes or no? Starting from x equal to minus a by 2 to x equal to a by 2. And this would moment of inertia about AA. Yes or no? Right? This would be 1/12 ma squared. This would be 1/12 ma squared about this axis. B will get cancelled. X square, when you integrate x cube by 3, when you supply these limits, you get 1/12 ma square. Right? Bolo, confusion hai? Suppose the same one, I want to calculate about BB. What would be I about BB then? 1/12 MB squared, precisely so. I about BB, this is AA. I about BB is going to be 1/12 mb squared. Right? I about this length about this axis is going to be 1/12 ma squared. I about this axis passing through the center of mass would be 1/12 mb squared. Suppose I want to find I about an axis perpendicular to the plane of the lamina and passing through the center of mass, what would I do? Perpendicular axis theorem. I about BB plus I about AA would give me I about an axis passing through the center of mass and perpendicular to the plane. Yes or no? So I about an axis passing through the center of mass and perpendicular to the plane from parallel axis theorem is going to be IAA plus IBB. 1/12 m a squared plus b squared. Sounds all right? बता रही धीरे 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 धीरे. Suppose instead of a rectangle it was a square. Then all that is required is A equal to B. Hello? So if this was the center of mass axis this way, then I about the center of mass axis perpendicular to the plane is going to be 1/12 m a squared plus a squared, which is 1/6 ma squared. Hello? Please shut up. Right? Now, this is a square plate. Square plate. Suppose I want to know I about this diagonal. I about this diagonal AA. Suppose I want to know I about the diagonal AA. Hey, can I say I about AA is the same as I about BB? There is no difference between the two diagonals of a square, right? And the two diagonals are also perpendicular to each other, right? So I about this is going to be I about AA plus I about BB from perpendicular axis theorem, right? So I about this axis ICM, that is, we've obtained this 1/6 ma squared, that's going to be I about AA plus I about BB. But from symmetry, I about AA is the same as I about BB. So that's twice I about one of the diagonals AA. So I about AA is going to be 1/12 ma squared. So I about any diagonal is 1/12 ma squared. In fact, let me see, let me tell you one thing. I about this axis we've obtained as 1/12 ma squared, right? Now let me tell you that if I rotate this axis and get another axis BB, if I rotate this axis by an angle theta and get this axis BB, let me tell you, and I will leave you with this thought today. Feel happy. Nothing will change. I about BB will be the same as I about AA. The mass distribution will not change. Think about it. I about this BB will be the same as I about AA and will turn out to be 1/12 ma squared. I about this BB will also be 1/12 ma squared. Yeah, absolutely. Yes, will be the same. Therefore, if you take any axis passing through the center of mass, be it the diagonal, another diagonal, or any other line passing through the center of mass in the plane of the lamina, I about that is going to be 1/12 ma squared. This much for today. Have fun and stay out of trouble.